Good afternoon, ladies and gentlemen, and I'm very pleased to be able to welcome you to this session. Just before we start, what you've been looking at whilst waiting to start there, that's a live stream from CERN showing you events as they occur. You can download that on the web anytime you want to have a look, and somewhere buried in that, you might even see a Higgs particle being produced. So this has been a momentous week for science with the discovery of the Higgs, which I personally think is the greatest discovery in physics for the last 80 years. And I'm delighted in this session to welcome Professor Rolf Heuer, who is the Director General of CERN, to Ireland and to this conference as well. Now, this talk was organized about a year ago, and in December last year, Rolf went on record very bravely as saying that we would find the Higgs by the end of this year. But I said to him, okay, he'll correct me, but I said to him, can't you hurry it up a bit, because we have this wonderful conference in Dublin. And he did his best, and he came in a week ahead, and so here we are, so that's fantastic. Now, I'm not going to give you a potted bio of Rolf, because you can read that in the program, but what I would like to say is that from my experience working at CERN, that the discovery of the Higgs is due in no small part to Rolf's leadership. And you really have to work on the subject to be able to say that, I think, to know what goes on. But he's provided an environment at CERN that is second to none in the world. It really allows scientists and engineers from all over the world to work together and collaborate effectively, so that this discovery is really a global discovery. And for that, I'd like to personally thank him, as well as introduce him to you to speak today. So Rolf Heuer, ladies and gentlemen.
Thank you so much, Ronan, for this very kind introduction. The search for a deeper understanding of our universe at the Large Hadron Collider, the world's largest particle accelerator. Well, unfortunately, I can't spare you. You will now get a lecture on particle physics, which means afterwards you are experts on particle physics. But before I do that, I just have one transparency on the mission of CERN. What is the mission of CERN? The mission of CERN is fourfold. Research, it's clear, it's our raison d'etre, why CERN was founded. You cannot do research without innovation. And you cannot do research without education and training, and you cannot do it alone. And therefore, CERN is an ideal place to unite people. Science is a universal language, and this we speak at CERN. We leave politics out, we speak science. So, in the research, we want to push forward the frontiers of knowledge. We want to understand the beginning of the universe. How did all this happen? That we want to find out, and that is what is intriguing us. In order to do that, we have to develop new technologies for accelerators, for detectors, and also for information technology. And you might wonder why I have the web here. Yeah? I mean, people who are below 20, they have never seen a world without the web. They might think the web was created at the Big Bang. This is not true. The web was born in 1989 when our experiments became so global, so international, that we needed a software platform to make information available to everybody all over the world who had the right to access it. That was the birth of the World Wide Web. We train scientists and engineers of tomorrow, and every country needs scientists and engineers of tomorrow. And I think this is a key message. You need more scientists, more engineers to keep the world stable, to keep a good world, and to keep science in society. So this is absolutely important. And as I said, we unite people from different countries and cultures. We have, I think, 99 nationalities registered at CERN. So this is a fantastic environment and a very nice environment. Okay, so one of today's scientific challenges to understand the very first moments of the Big Bang. Yeah? From the Big Bang, when the universe was hot, spot-like, point-like, tremendously hot, and then it expanded over roughly 14 billion years until where we are today in a rather cool universe, and from 0 to 10 to the 28 centimeters. I don't know. I don't know what 10 to the 28 centimeters mean. It's very large. Maybe it helps you if you replace the centimeter by dollars. You have roughly the square of the American deficit. it only helps me to understand that the deficit is pretty large. Okay, so it's very difficult to understand these, or to imagine these sizes. So here you have it on a ruler from the Big Bang to today, from essentially 0 to 10 to the 28. As difficult as it is to imagine the large scales, it's also difficult to imagine the small scales. From a certain scale on, everything for me is roughly like 0. Yeah? So it's very difficult to imagine, but mathematically and in the development of the universe, it's a huge difference between these different digits. What we can imagine is usually the human size, or close to the human size, and who in the audience knows who that is? It's Ernest Walton. And the Irish people should not forget that Ernest Walton was a famous scientist and one of the key persons in the accelerator business, yeah? Cockcroft-Walton, yeah? So you should not forget, and you should not downplay your influence on that. Okay, so how to study the universe? Well, we can look into the large scales. With space-based telescopes or ground-based telescopes, we can look into the history of the universe. But we don't come closer to the Big Bang as roughly 400,000 years, because the universe was so hot that photons could not escape. They were always ionizing the atoms which tried to form. So 400,000 years, which is pretty close to the Big Bang. You can also go to the small scales. Now here you need a super microscope, and the Large Hadron Collider is nothing else than a super microscope. Okay, and with this super microscope, you come down to distances like 10 to the minus 16 centimeters, or in time, you come as close as 1/millionth of a second. Nobody else comes closer to the Big Bang than we with our super microscope. This is in human terms a very, very short distance, a very, very short time. However, in the timing of the universe, tremendous amount has happened in these millionths of a second. So we still have a lot to explore there. Okay, what is the role of accelerators? Well, if you want to resolve the inner structure of matter, you need to resolve very tiny objects. In order to resolve very tiny objects, you need small wavelengths. So you have to have a high resolution power. Unfortunately, small wavelengths means large energy. There's nothing about it. You need large energy. But with this large energy, according to Einstein, you also have the chance to produce new particles with high masses. So the high energy gives you a high resolution power and higher mass new particles. This is the nice thing at the accelerators. And when you produce new particles, for example, you can produce them in high statistics. That means you can do precision measurements. Cosmic rays have also high energies, but very low statistics. So you cannot do really high precision measurements. Okay, so when we study the physics law of the first moments after the Big Bang, we have a symbiosis between the smallest, particle physics, the largest, which is astrophysics and cosmology. And this is the intriguing thing today. I mean, this is a fantastic science field which really spans the smallest to the largest and which gives you information about the early universe. Okay, so what have we learned over the last 100 years? Well, Rutherford 101 years ago told you that you are essentially all empty. You might not realize this, but it's true. Because the atoms are dividable, so they have the nucleus, the nuclei, and then the electrons around it. Now the nuclei are built out of protons and neutrons, and these protons and neutrons in turn are built up out of quarks and gluons. So they are composite objects. So we have come from an atomos at that time to the new atomos, namely the quarks, gluons, and the electrons, which are point-like particles. These are the smallest constituents of matter. And now let's look into that, what we have learned here. It took us roughly 50 years to establish the status of the Standard Model. The physical world is composed of quarks and leptons. And you see it here, 3 families of 2 quarks and 2 leptons each. So the first family here is the up and down quark, and the 2 leptons are the electron and its neutrino. And that's enough. You all consist only of these 3 particles. And me too, of course, but up quark, down quark, and the electron. That's all. That's all we need to form us. That's enough. Now nature has decided to make a second family, charm and strange quark and muon and muon neutrino, and even a third family. And the only difference between the 3 families is that the corresponding partners here along the lines are heavier and heavier. So the top quark is the heaviest elementary particle we know. It's a point-like particle, and it's as heavy as a gold atom. fantastic. Now we don't know why we have three families. We don't know why the masses are so different in these three families. So we know a lot, but we also know nothing about these things. So but it's fantastic here. That's the periodic system of the microcosm. 12 entries. It's much easier than chemistry. Yeah? You only have to know 12 of these things. Plus, of course, these matter particles have to exchange forces. They have to know which forces come from the other particles, and these forces are interchanged, mediated by bosons, by gauge bosons, by the force carriers, the photons for the electromagnetic force, the gluons for the strong force, and the ZW for the weak force. The graviton we can neglect because gravitation is so weak in the microcosm that we can fortunately neglect it. So that's all we need to know about the particles. That means the force particles and the matter particles, plus, of course, the corresponding antiparticles. 85 years ago, Dirac introduced antimatter, which was then 80 years ago discovered. And particles and antiparticles are always created in pairs. You see, according to Einstein, E equals mc squared, you produce out of the energy always particle and antiparticle. But also, when they meet again, they annihilate each other. So mass goes back to energy. That means there's a question. Why are we at all here? Because at the beginning, matter and antimatter were produced or created in equal quantities. Now, in equal quantities means they annihilate again, and we would all be energy. But nature has introduced a very small asymmetry in the behavior between matter and antimatter, so that there's, at the end, 1 part in 10 billion more matter than antimatter. And this 1 part in 10 billion, this tiny distortion, is sitting here and standing here. That's it, because there is no sign of antimatter in the universe. So we are a matter-dominated universe. That's one of the big questions. How did that happen? So that was the static model of the static behavior of the static model of the universe. The standard model of the particle physics is now a mathematical formalism which describes all the interaction between these particles through the weak, the electromagnetic, and the strong forces. And we have tested this model with a very, very high precision, down to a size of 10 to the minus 18 meters, or energy-wise up to 100 GeV. And this beast withstands all these tests. It's fantastic. It's great. It's really a fantastic achievement. And I have now one transparency where I show for the scientists the achievement. That's here. Don't worry too much. These are 17 quantities which you can measure, for example. Now, if the quantity is exactly in its measurement on the value which is predicted by the standard model, then the point is at 0. If it is a normalized error, 1 normalized error away, then it's here. 2 normalized errors away, 3 normalized errors away. And you always have measurement errors. So you have a distribution of measurement errors, and you expect something like this. You expect more which are below 1, a few which are between 1 and 2, and from time to time 1 which is between 2 and 3. This is absolutely normal. Actually, without this point here, which is deviating 3 normalized errors away, without this point, the fit would be too good. You need that, yeah? So, I told you, it's a fantastic achievement. On the other hand, it's absolutely frustrating, because there's one cornerstone missing within the standard model. Well, at least until a week ago. I soon have to change the whole talk. And this is a question, what is the origin of mass of elementary particles? Because the standard model as it was introduced originally was only valid for massless particles. But we know the particles have all mass. And then you need a second formalism, which you plug into the first one. And with this second formalism, you make the standard model valid also for massive particles. And this was Mr. Higgs, the physicist Higgs, plus others, who introduced this second mechanism. And this second mechanism can be explained as follows. Mass is not only a question of weight, it's also a question of velocity with which you move once you have a certain energy. This is my last equation, by the way. if you have a mass 0, then you move with the velocity of light all the time. If you have a heavy mass, then you're moving more slowly. And the heavier you are with the same energy, you move more and more slowly. So the higher the mass, the lower the velocity. So what these guys did, they introduced a field, a scalar field. A scalar field is a field which has no preferred direction. How can I make this a bit clearer? If you swim in a river, then depending in which direction you swim, the force of the water is different on you. Yeah? So that means this is a vector, usually. If you swim in a large swimming pool, then the force of the water is everywhere the same, independent in which direction you swim. That's a scalar. Okay? So they introduce a scalar field, and the particles which move through this scalar field, they acquire mass through their interaction with this field. And the stronger their interaction with this field is, the more massive they are. And this field has a peculiarity. It can interact with itself. It's difficult of a swimming pool, but it can do that. And the self-interaction of the field, this is the famous Higgs particle. This is a signal that this field is existent or not. Okay. This is a Higgs field. Or it's a party of journalists, cocktail party. They are all equally distributed in the room. I come in here and want to go through here massless. That means with a velocity of light. That's easy because they don't know me, so I'm through. But then somebody comes in whom they know. What happens? They cluster around him. They cluster around him. He acquires mass. Yeah? He's hindered in his velocity. The more known that person is to the journalists, the more journalists are around him, the more massive that person gets. Yeah? So this is the way a particle gets mass in the Higgs field. How to explain the Higgs boson? Well, suppose I open the door and I whisper a rumor into the room. The journalists, of course, are curious. What did he say? That's a self-interaction of the journalists, or the self-interaction of the Higgs field, and this is a Higgs boson. So, particle physics is really easy. Okay, now we know the Higgs particle is the last missing cornerstone within the standard model. And we know everything about it. The only thing we did not know is if it exists. Slight problem, but maybe we have solved it. I will come back to that. Okay, but this standard model leaves many, many questions open. For example, can we unify the forces? This is here the energy scale. Here's a Big Bang roughly. And the standard model, these are the dashed curves, cannot unify the forces at the high energies. If you introduce a model which is beyond the standard model, then you can unify the forces. The standard model doesn't say anything what happened to antimatter. It doesn't tell us in how many space or time dimensions we are living. And it has not the faintest clue what is dark matter, what is dark energy. And the LHC will address most of these questions. So it goes much beyond the Higgs particle. In particular, it will address the question of the dark matter and dark energy, because the standard model merely just doesn't explain. It describes 4 to 5% of the matter energy density in the universe, the visible universe. The 95% are dark. 1/4 of it is dark matter, which clumps and tries to keep the universe together and shape the universe at the beginning of its existence. 3/4 of it is dark energy, which drives the universe apart. We know very little about dark matter. We know essentially nothing about dark energy. But I think with the Large Hadron Collider, we are now entering the dark universe. And this is fantastic in the next years. So the Large Hadron Collider, I think it's one of the largest instruments ever built, 27 kilometers of circumference here in the nice region of Geneva, 100 meters underground. more than 10,000 people involved in design, construction, and now exploitation. It collides protons, that means the nuclei of the hydrogen, to study the very beginning of the universe, and that we do 40 million times a second. It's quite often. So how do we do this? Well, we have in this tunnel 2 pipes in the magnets, the blue and the red one. In both pipes, we accelerate protons, 2 beams of protons in bunches. Yeah, we have bunches of protons. So here are 100 billion protons are in each of these packets. And these 100 billion protons, they are in one packet, are brought to a collision at 4 points. And in these collisions, sometimes the protons collide, but the protons are composite particles. So it's not the protons which are important, it's the quarks or the gluons out of these protons which are interacting, getting rid of their energy, so you have an energy spot, and then out of this energy, new particles come out, and we have to measure these new particles with our experiments. This is how it was built. This is one of these 15-meter long magnets, brought down, and then in the tunnel, brought to its place where it should be installed, then being installed, aligned, and then you have 10,000 of these high current, 15,000 amperes, high current connections, which have to be braced and soldered. And then afterwards it looks like this, and this is how I like to see it, because then we can take data. Then it's ready to go. It's one of the coldest places in the universe, because these 27 kilometers are driven at superfluid temperature, or superfluid helium, 1.9 Kelvin above zero. The outer space is 2.7. So we have the largest refrigerator in the world. At the same time, it's one of the hottest places in the galaxy, because at the collision of the protons, we produce temperatures which are much, much higher than those in the center of the sun. How can that happen? Well, if a proton hits another proton, that's like a mosquito in full fly hitting another mosquito in full fly. You agree with me, with 2 mosquitoes hitting each other, you don't come very close to the Big Bang. What's the key? The key is that these protons are tiny, tiny, tiny particles. So the energy density, that means the energy divided by the area of the protons, is huge. And this is this energy density which brings you so close to the Big Bang. Okay, so the design energy is 7 on 7 TeV. Today we run at a bit more than half of this energy, 8 TeV. We have 1,400 of these packets running clockwise, 1,000 running anti-clockwise, colliding at 4 points. That means we have at the moment a 20 megahertz crossing rate. And we have a luminosity, which means the probability of collisions per second, which is already today beyond the design value. Now imagine such a huge collider, which is a new thing, which is a prototype in itself. After 2 years of running, you exceed your design value. I'm not sure if any other accelerator did this so quickly. I mean, it's fantastic. Okay, and you have many, many interactions per second, per crossing per second. So you have 10 to the 9. That means, I think it's a billion proton interactions per second. In each collision, you produce many hundred charged particles. It's an enormous challenge for the detectors to see that, yeah? To take the pictures of that and to collect the data, to store the data, and to analyze the data. Okay, so 2010, when we really started, we entered a new era in fundamental science. 4 big experiments and 3 very small ones. And you might wonder, why 4 experiments? Well, we have 2 general purpose detectors, CMS and Atlas. And a message to everybody: never believe a scientific result which comes only from one group. It always has to be cross-checked. It's very, very important. And this is also why we have, fortunately, 2 of these general purpose detectors, which are supposed to record everything which is interesting. Then we have a specialized detector to study B quarks. Our chairman is part of this experiment. That means Dublin is part of this experiment here. This is studying the question, where is antimatter gone? Yeah? So this is addressing the question of the difference between matter and antimatter. And finally, ALICE, which is a specialized detector to study not the proton collisions, but from time to time, 1 month per year, we collide lead ions in order to create or produce the very hot, dense matter short moment after the Big Bang, and they study that hot, dense matter. But there's overlap in physics reach between the specialized and the general purpose experiments. Some particles can live a bit longer, and they leave traces a little bit longer. And the specialty is to find these heavy particles which live a little bit longer, because they could be a key to the antimatter question. And LHCb does this, but also the other experiments can do that. So there's overlap here, and also overlap in physics reach with the heavy ion experiment, because all of these experiments, they can reconstruct, they can see several thousand trajectories in one of these events. Several thousand to reconstruct it, to measure it. And actually now comes at halftime when always has a commercial, I think. I put now a commercial in. This here is a book, and you see that's like the cover is like this. This is a real event, the real event display of one of these collisions. This is a book with fantastic photos. I can tell you, this is Peter Ginter, very, very well-known photographer, and I took the trouble to bring a few books here. So if somebody has too much money, I'm happy to sell some of these books. Otherwise, I have to take them back. Okay, and I don't think you want to do that to me. Okay, but I can tell you, it's very nice books, and it explains also in layman terms what these things are and how they are made, etc. So it's a nice book. Okay, over with the commercial. So the versatility of the LHC and the complementarities of the experiments makes the whole of LHC much more than the sum of its parts. So these 4 experiments together are much more. Okay, and one of it, I want to show Atlas again. It's one of the largest and most complex detectors, and you see the size here. This is the size of an average physicist or average technician. Okay, some of you got the joke. 20 times 20 times 40 cubic meters. And in the whole volume, the trajectories of the particles are measured with an accuracy roughly like the diameter of the human hair. In the whole volume. Would you agree with me that this is engineering art? No, yes. What's that? You see the 8-fold symmetry, you see the support, you see even these red things here. It's very similar, isn't it? Well, this is a stage design of an opera. And I can tell you Atlas was before. So it shows you how much interest also from artists is there in our science, in the science and in the engineering. So this is fantastic to see. And therefore, I have decided a year ago to introduce a new program, not only to collide particles, but also to collide artists and scientists. And therefore, we have introduced a new program, Artists in Residence Collide at CERN. And it's amazing. We started this year, and the first program was for digital arts, and we got nearly 400 applications from artists. And the first one came beginning of the year, and these artists get then a scientific counterpart. And it's fantastic how they interact. So completely different personalities, and they interact fantastically. So 25th of September, I will see the first result of this collision. And I heard from the artist that he is inspired for 10 years at least. So fantastic. Okay, now back to physics. Now if 2 protons are colliding, you don't know which of the quark or gluons in the one proton collide with which quark or gluon from the other proton. For example, you can have the so-called bread and butter physics. For example, 2 quarks colliding, and then again 2 quarks producing, and these 2 quarks have to go back to back for momentum conservation. And then you have 2 jets of high energy going out back to back. And if you roll out a detector like this, you see very nicely one jet of high energy, the other jet of high energy back to back in this plane. So this is the fantastic proof that they can measure all of this. Of course, you are more interested in new physics. So what could be the new physics? Well, for example, 2 gluons could fuse, and then you could produce the Higgs particle. And it could, for example, decay in 2 Ws or 2 Zs. Very striking signature here. It's a very rare process, unfortunately, but these are the processes we are looking for. But it's very rare. You see, these are, I think, 12 orders of magnitude. And this is the probability of all the processes which could happen. And then you go down order of magnitude until you are here at the Higgs or the new physics. So the problem is more than 10 orders of magnitude difference between the normal physics and the new physics. So what we have to do, they have to select one out of much more than 10 billion of the collisions of these processes in order to come to the new physics. It's not looking for a needle in a haystack. This is looking for a needle in many haystacks, with a slight problem that the haystack consists out of needles. And the needles have a slight difference, and that's the problem. You have to find the needle with a slight difference in many, many other needles. And that means we have to produce collisions. And 2010, this is a measure of the collisions. At 2 here, I think you are at 200 trillion collisions. In green is 2010, so that's very little. That was a startup. In red, we delivered already quite a bit to the experiments, much more than we promised. We are sometimes very careful with our promises, not concerning discoveries, but concerning other things. And 2012 now, it was a rocket year up to now. You see how much we produced in the beginning of the year. So many more collisions. The problem is, if you deliver more and more collisions, you have to squeeze these packets more and more so that more protons collide with each other because you are current limited. You cannot put all the time more current into. You have to squeeze these protons together. And that means these experiments in one packet collision have many, many interactions of protons. Here you have 20 interactions of the protons. But for example, these yellow tracks here, these trajectories are coming from this one vertex. So you can identify all of this. And this is going fantastically. I mean, that the experiments can do this so quickly and so precisely is also a miracle for me, although I'm an experimental physicist, or I was it. Okay, so what do you do with it? Well, here is the timeline in integrated number of collisions. Here you are at 100 trillion, for example. Here is the physics as a function of this time. So if you have very few collisions, you just look at the bread and butter physics, the normal things. And then you start to look into the standard candles of particle physics, the W, the Z, the top, etc. So the more collisions you have, the more precisely you can test the standard model. And before you have not proven that you understand the standard model, the physics of the standard model at this high energy, you cannot claim a discovery if you see something else. You have first to prove, I see the old stuff, before I can say, I see some new. So today we are here at the possibly new stuff. And that shows you on one transparency the beauty of what these experiments did. These are different processes with our standard candles, WZ and top quark, for example. And in orange is the standard model prediction, and in black are the points of the measurement. So fantastic agreement between the prediction of the standard model and the measurement, despite the fact that you have here 5 orders of magnitude difference in production probability of these processes. So this is a fantastic agreement between experiment and standard model. That means an excellent performance. In 2010 and 2011 together we had 500 trillion collisions. And this shows again all our standard candle on one transparency. It was the rediscovery of the standard model until 2011. And now, after the journey through the standard model, the experiments are now taking us into new territory. And what is a new territory? Well, still, this unfinished business of Newton, what is mass? We don't know how it came about. Why is there no more antimatter? What was matter like within the first moments of the life of the universe? And the little embarrassment, what is 96% of the universe made of? Yeah? Okay, let's first look into the question of why is there no more antimatter? Now, this shows you how you can study antimatter in the experiment, which Ronan is part of in LHCb. This looks complicated, but I think one can easily explain how you see a difference, even by eye, between matter behavior and antimatter behavior. So this is so-called B meson, which can decay into a pion and a kaon. The anti-B meson, it's always with this bar on top, can also decay into a kaon and a pion. And then you look into the probability how often these decays, and then you see here the red one, it's normalized. You see in red, the particle decays more often into K and pi than the antiparticle. So there is a difference between particle and antiparticle. Yeah? You see it even by eye. And then you see the blue is a full spectrum, and you see there's a shoulder in blue. Then you go to a special B particle, the B sub S, which contains a strange quark also. That's in this shoulder. Now you look into this shoulder here, that's a green one. And you see in the green one, the particle decays less often into pi k than the antiparticle. You see that decays much more often. The probability is higher. So you see by eye a difference between matter and antimatter. And these things you have to study in great detail. This is predicted by the standard model. So up to now, there's excellent agreement with the standard model because this is what they had to find. But now they look more deep into it, and the first evidence for new effects they might have seen not in the big sector, but in the charm sector. This is, for me, the first possible evidence. So it takes time to do all this, but I hope I made it clear how you look into these differences. You look into asymmetries of these things. Okay, so now we can come to the question, what is mass? And what is the dark universe? And I hope that you are now ready together with me to enter the dark universe. Let's start with dark matter. It's obvious that 25% compared to 5%, that dark matter must have had a dominant role in shaping the universe at the beginning of its life. And astrophysics, astronomers will tell us how it has shaped it. But only at particle accelerators you can produce dark matter in the laboratory and understand exactly what it is. Is it composed of a single kind of particle, or is it rich and varied like the normal world? The LHC may be the perfect machine to study dark matter. And what is a good candidate? A good candidate is supersymmetry. Supersymmetry introduces for each standard model particle a shadow particle, a supersymmetric particle. It unifies in this way matter particles, matter and forces, because for each matter particle it has a force counterpart, for each force particle it has a matter counterpart. You might say, okay, if the physicists don't know what to do, how to explain things, they double the number of particles, and they can explain everything again. But don't forget, 85 years ago, Dirac introduced antimatter. And with the introduction of antimatter, he doubled immediately the number of particles, because each particle got an antimatter particle. So the number of particles were doubled, and we got a huge amount of knowledge out of this. And not only that, 40 years later, and that means since 40 years, we are using antimatter in the hospital. For diagnosis, whatever, we use it because PET scans, positron emission tomography. The positron, the P, is the antiparticle of the electron. So we are using antimatter in the hospital. I'm not saying that in 40 years we will use supersymmetry in the hospital, but what I want to say is that you gain a lot of knowledge. And you know it can be used at some stage, even for practical purposes, but you don't know when, and you don't know where. And this is what politicians have to understand. Well, some do. Okay, so that's supersymmetry. It allows to unify the forces here at the high energy. And it provides a dark matter candidate. Why? Because these supersymmetric particles, they are not stable. They decay into supersymmetric particles and normal ones. They decay, until the last one is the lightest supersymmetric particle. He doesn't find a partner, so it's stable. And that is a candidate for dark matter. Okay, so this is, for those who are still awake, this is the standard model again with the three families. The force particles are now the Higgs added, and this is the supersymmetric world. Each one has a counterpart here. And as I said, could be produced at the Large Hadron Collider, two supersymmetric particles decaying into another supersymmetric plus a normal, supersymmetric normal, etc., until you reach the lowest mass supersymmetric particle. stable, escapes the detector. So you're looking for missing energy and missing momentum. And this is the way how you could possibly identify dark matter candidates. This is complicated, looks complicated. And you don't have to look at it in detail. What do I want to show with this? Supersymmetry is not one symmetry. Supersymmetry is a plethora of models, of different models. And each model has a different way of expressing which one would be the lightest supersymmetric particle. And this is just a few of these models, and it shows you where the limits of one of these experiments is for the lightest supersymmetric particle, for example. And you see it ranges from 100 GeV to 1 TeV. So for some of the models, the so-called constraint models, the air is getting thinner and thinner. However, there are so many supersymmetric models that there are many possibilities to still measure, identify, and find supersymmetry. The potential for discovery of supersymmetry is sizable, even now at 8 TeV, and of course even more in the next years when we are going up to 14 TeV. But it shows you what tremendous progress the experiments have made going to really high mass particles, which they can already exclude. So the theorists have to be careful because they are attacked by the big experiments and also by LHCb, which is a smaller experiment. I chose this transparency because I think that the guy here survived, and I want our theorists also to survive because I have to give us some guidance what to do next. So the LHC results should allow to do the first discovery in the dark universe. The problem is still 73% of the universe is this mysterious dark energy, which is evenly spread. Yeah? It's a scalar because the universe expands in all directions equally. So it's a scalar again. That's interesting. But the challenge is to get first hints about the world of dark energy in the laboratory. That's a real challenge. And there I come to the Higgs. Because the Higgs is different. And this is a very important thing. And this makes the discovery of last week so important. All matter particles have a spin. All force particles have a spin. The Higgs has no spin. It's a spin zero. It's a scalar. It's different. It's neither matter nor force. It would be the first fundamental scalar ever discovered. We have never had a fundamental scalar in our hands. And this could be the clue to the DNA of the universe, so to speak. The key to the DNA of the universe. And the Higgs field fills the entire universe. It's a scalar. Dark energy is a scalar. They are not the same. That's my disclaimer. They are both not the same. But studying one scalar could give you some idea about the fact how other fundamental scalars behave. And therefore, you could learn a lot, maybe, about dark energy. The problem, again, is, here you remember this is the total probability for producing something at the LHC. The Higgs is very low down. In addition, this Higgs particle can look completely different in the detector. Yeah? Depending on its mass, it has different ways of decaying, yeah? Into WW, ZZ, gamma, gamma, whatever. So it's a tedious job. Imagine you have the job of identifying some special snowflakes in a huge snowfall. So you have to take many pictures in order to select a few of these snowflakes. The problem is this huge snowfall is in front of a snow field. And this is the same challenge here. Yeah? You have a huge background like the snow field and the snowfall, and you have to find these special snowflakes called Higgs, depending on how they look like, how the Higgs decays. And this shows you what is the problem. These are all the different ways the Higgs can show up. And you see in black is always the snow field or the snowfall. And in red is what you would expect from the Higgs appearing. So very tiny signal above a huge background. You see, it's very difficult to look into one of the channels to see something. You have to combine all these different channels in order to finally see something. A very promising channel is this one, where the Higgs goes into 2 photons. This is a in principle, very clean channel, but with a huge amount of background again. But the events would look like this. This would be a striking signature, yeah? many, many trajectories of charged particles, and then two photons with a huge energy, one here, one there. This could be a Higgs particle, or so one of these special snowflakes, or it could be part of the normal snowfall. And the problem is to separate this. And that was the status of at the beginning of July on the Higgs search. You see, this is a mass of the Higgs boson because we don't know the mass. And whatever is below the line of 1 is excluded. So you see here, everything is excluded. Now you zoom in here into the low mass, and you see in the low mass here, there is something. There's something which you cannot exclude and which goes pretty much above. That was intriguing. And the official language we used was intriguing fluctuations. And one should say that it took roughly 30 years to restrict the mass to beyond 114 GeV. 30 years. Within 1 year of data taking, the experiments excluded the rest of the time of the mass range. Fantastic. Within 1 year. I would never have expected that, although I'm an optimist. So, only this small window is open. But what is the status of July 4th? This shows you in the gamma-gamma part, in the decay into two photons, here the background, and then on top of this you have a very nice signal, and this could be the Higgs particle at around 125 GeV. So this is how you dig out the evidence for this particle. What is very striking is to see how this developed over the past 12 months. Now here you have, this is the probability value, therefore it goes down here. The further down you have something here, the higher the significance you have that it is not a fluctuation of the background. And we need a 5 sigma in order to claim discovery. So this was a year ago at the conference. You see there was wiggling around everywhere here in the mass range between 110 and 150 GeV, with some more wiggling here. Then in December we had a seminar at CERN. There were two things. First of all, this became deeper and therefore more striking. And also the other wiggles were more or less gone except of here. So everywhere it's straightened out except at that one point. Then a few months later, with the same data, it got away a little bit here after refined analysis, but not very much. This is what you expect usually from fluctuations. And this is where we are today. Striking signal here, very nice flat here, everything, only here something is left, with 5 sigma now. And since we have 5 sigma, the Director General can say we have a discovery. But you see how this very nicely evolved here. Everything went away except this one signal which you saw before also in the gamma-gamma sector. So, we have it. Yeah. I said as a concluding remark of the summary, as a layman I would say we have it. As a scientist I must say, what do we have? And this is why it's only the beginning. Yeah? The discovery is only the beginning. What is next? Well, you have to see, does this beast have the properties which you expect from the standard model, Higgs? I mean, we have to measure many more than these decay channels. We have to see, does it really interact more with the heavy particles than with the less heavy particles? So we have to measure all these channels here with very high precision. We have to measure the properties of this new particle with high precision, and that will take us years. Yeah? We have to see, is it a scalar particle? Then it would be the first fundamental scalar. I very much hope it is. But is it the Higgs boson? Or is it part of a family of Higgs bosons? Because supersymmetry requires at least 5 of these. So we have to see. That will be the work in front of us. But studying the properties could give us information on dark matter, and it could give us first hints on dark energy. So this beast, when we call it Higgs boson, when it is a Higgs boson, it brings us really into the dark universe. And I must say, our understanding of the universe, to my mind, is about to change, because we have now something virtually in our hands with which we can study much more on the beginning of the universe. This is why everybody got so excited last week. It was fantastic. I only start now realizing what we did last week. It takes some time to sink in. I think we have something great in hands to study in the next years to see how the universe was shaped. So, these results will help us to study the Higgs mechanism in detail. It would be the first investigation of a scalar field, as I said. And this could be the very, very, very first step to understanding dark energy. I think that's great. And this is what we have to do, looking into my crystal ball. We have a predictable future of roughly 20 years for the LHC. We are now here taking data, then we shut down for 2 years to make the machine fit for higher energy. Then we run again, then we give it a pause, run again, give it a pause, improve it, upgrade it, and collect data until we have, I cannot translate it into how many, 300,000 or whatever trillion collisions. Many, many collisions. So we have a clear program over the next 20 years for this. And what will we do? We will study the properties of the Higgs boson and, of course, physics beyond the standard model, because there's still a lot open which we should try to find out directly what is beyond the standard model. Okay, so the past decades saw precision studies of just 5% of our universe. And that was the discovery of the standard model. The LHC delivers data in a very nice way. I think today we are just at the beginning of exploring 95% of our universe. And I can only say the future is bright in the dark universe. Thank you.
So thank you very much, Rolf, for that fascinating and broad-ranging talk covering some of the big questions confronting us in physics today and how the LHC can answer them. Now, I think we have a little bit of time, and I'm sure you'd like to ask some questions of Rolf. So, do we have any? We have people going around now. If you want to ask a question, put up your hand, and somebody will find you and give you a card to hold up, and then I'll call out a number, and then you can ask your question with the microphone.
There's number 4.
Okay, number 4 over here.
Hello, I'm Stefan Jungbild, I'm a biologist. Just a more general question. So I think what we do, biologists, is really simple compared to your things. We do simple experiments, get results, and we can put things together. And I think in terms of images, I can really understand. I imagine cells, DNA, animals. So I was wondering, how do you think? I mean, what you do, can you imagine this in terms of images, or do you think in formulas, in mathematics only? Is this really, for me, this is so complex, this is beyond my understanding really, but can you transform your physics world in something image-wise? Do you understand this apart from mathematics?
Well, I try to do it, for example, with a party of journalists. It's very difficult. I usually try to find examples, metaphors, etc. We are improving. It is difficult. We can show striking figures, striking photos. But sometimes it's difficult to really translate it into a thing which catches, which is really visible. Yeah? It is not so easy. The only things I have are on here. Well, sometimes I have a few more, but I try to improve every day in that. And the way we think is very difficult to.
Okay, we have question number 2 over here.
Do you talk to people who are studying low temperature physics, so the people who are looking at Bose-Einstein condensates and superconductors, because they are coming from the very low energy side of the universe? And is their data complementing yours, and can you work with it as well?
Well, our theorist friends, of course, talk to them, and we are using Bose-Einstein condensates, we are using the Higgs boson. So we are using a lot of these things. And actually, the superconductivity and the Higgs mechanism is very similar, yeah, the Lorentz pairs, the Cooper pairs. But to use it and for these questions which we have, I would say, is very difficult. I think that's very difficult to use it for us. But the theorists talk to each other because the models are very similar. There's one, there's one.
We need a microphone perhaps down here.
Hello, yes. I'm a physics teacher, and I just want to say congratulations on all your wonderful achievements at CERN. It's just amazing. And I want to go back to the analogy of the journalists as well. I really loved it, because I was trying to explain the Higgs field to a group of non-scientists in the pub the other night, and if I'd had your journalist analogy, it would have been great. But one thing that struck me about it was that you had the rumour that whispered into the room, which sort of implies an event that causes the journalists to interact with each other. So I guess my question is, what causes the Higgs field to interact with itself?
Well, I think it's a vacuum fluctuation, essentially. Yeah, it's a fluctuation of the energy which does it. I don't think I can go into much more detail here, but it's a vacuum fluctuation, essentially. But you have to have the energy, yeah? So that means up to a certain point, the universe was hot enough to do that. But when it cooled down, it couldn't produce any more Higgs particles because the energy was not high enough. Now we can do it again.
Thank you.
Number 4 over here.
It's a political question. Have you been approached by the Irish government in relation to membership of CERN recently?
The word approached, I think, is the wrong one. Well, we have started to talk about it. Yeah, we have started to talk. But I have been approached by other countries. Actually, I mean, we have really done a big step 2 years ago. We have redefined the E in CERN from Europe to everywhere. That means now also countries outside Europe can become members, and the first ones I hope I have end of this year. So maybe that helps Ireland as a European country, as a country in the Union. Okay.
Okay, do we have any last questions? Right at the back, number 6.
Hi. I'm just wondering, in your opinion, do you think that it actually is the Higgs boson, or could it actually be another unknown particle that you haven't discovered yet? Is there a chance of that, or?
Actually, I haven't understood a word.
Sorry.
Are you asking if it's a Higgs boson or something else?
Said, do you definitely think it is the Higgs boson, or could it just be some other unknown particle? Because have you examined any of the properties of it yet, or anything like that?
I told you, I don't know yet. It's a bit too early in the game. I mean, it will take a long time to really figure out the detailed properties. Let's put it this way: it looks intriguingly like the Higgs boson, at least like a Higgs boson. And once we have determined the spin and really found out that it's a scalar, then you can ask me again. Then I would say it's much more likely, yes, it looks very much like the Higgs boson. But I cannot yet, and I don't want to, exclude that it could be one of a family, which would be absolutely striking. Because in this family of Higgs bosons, the lowest mass one should look very much like the standard model Higgs boson. So, if you ask me professionally, I would say I don't know. If you ask me privately, I would say I think so.
Okay, I think we're almost out of time, so one last question up here, number 3.
I'd just like to say again, congratulations on your discovery and thanks for a fascinating talk. I'd just like to ask, and maybe it's too early, but is there any implications for everyday applications for this discovery?
Well, ask me in some years. Look, we are doing curiosity-driven research or basic research. The beauty of basic research is it has a target, a clear target of knowledge gain. And you gain knowledge. What we gain here with this knowledge, we don't know yet even what we gain here. The problem is that from the research itself, it's very difficult to predict when and where you can apply it. Yeah? I mean, this question is asked to everybody who does basic science. Also, hundreds of years ago. I mean, Michael Faraday was asked by his, I think, the finance minister, Mr. Gladstone, when he was looking into studying electricity. He was asked, Mr. Faraday, what can you use it for? Okay, the same question. And Faraday said, sir, honestly, I don't know. But maybe one day you can tax it. So, this is exactly what you can say, because you don't know when and you don't know where. But you are pretty sure, yes, you can use it at some stage. This is one thing. The other thing is that you can really tell, you can use the instruments, the technologies which you need in order to do this research, you can use very quickly in society, in the private life, or in the professional life. The best example is the World Wide Web. Yeah? It has changed our life. And it came out of this research, because we needed it. Yeah? High vacuum can be used for improving solar panels. We need the high vacuum. We had to invent new pumps. We did it. Or several examples, hadron therapy comes out of the accelerator business, yeah, to fight cancer. We are working on that too. So that comes out of the instruments which you use. But from the research per se, a priori, it's knowledge gain. And without this knowledge gain, we don't make progress. And without this knowledge gain, at some stage, you don't have the basis you lose the basis for the applied science. So I think one has to keep a balance and both things together. But the prediction is very difficult, and I think it would be very wrong to really give a prediction now, and in 20 years they say this guy was lying. I don't care then at that time, but...
Okay, well, on that optimistic note for how basic research can actually change our whole lives and produce a brighter future for us all, I think that's a very good place to draw this session to a close. So let us once more thank Rolf Heuer for a fascinating talk.